Okay, so today I'm going to be talking about Jacobians, which is chapter 14.8 in the Larson textbook. We've already kind of seen Jacobians before when we transformed Cartesian coordinates double integrals into polar coordinate double integrals. And in that case, when we do that, the integral from f of integral, sorry, dx dy becomes r dr d theta. And in this case, the Jacobian is r over here. That's the Jacobian. So before we actually go into this example, I'm going to talk about a more simpler example of what a Jacobian is through u substitution. Let's take a general integral of f of x dx. And let's say we're trying to do u substitution on this. So we have let u equals g of x, some other function of x. Let's do something a bit strange here. Instead of saying let u equals g of x, let's invert it. Let's say let x equals g of u. And we go through the usual steps. We say dx equals g prime of u du. And we substitute everything back into this integral. So this g prime of u becomes the integral of f of g of u times g prime of u du, which is dx. And yeah. So this is an example of why we can find Jacobians in stuff we've already done before. And in this case, g prime of u, that is the Jacobian. Jacobians are just an artifact of switching from one coordinate system to another when we're trying to do integrals. Let me give you a concrete example of what Jacobians are in u substitution. Let me move this off to the side so that we can have some more space. Okay, let's say we have the integral of x squared dx, and we want to shift this to another coordinate system. By shifting it to another coordinate system, I mean we're stretching or squishing the x-axis in a way that it makes it easier for us to do our integral. And in this case, when I'm demonstrating the Jacobian, it's not going to make it easier, but it's just going to add another term that displays what the Jacobian is. Okay, so we have, let's say, let x, since we have x here instead of setting x here instead of u, let x equals something like square root of u. We go through the process again. Du equals 1 over 2 square root of, sorry, not du, that's dx. 1 over 2 square root of u du. And so plugging everything in, we have x equals square root of u, so x squared is u, and dx is this whole situation here. Dx equals 1 over 2 square root of u du. And in this case, 1 over 2 square root of u du, that is the Jacobian of this coordinate system shift. And concretely, let's kind of visualize what this coordinate system shift is in using the x and y axis. Suppose we have just and the coordinate shift is x equals the square root of u. This is our regular coordinate system. X equals 1, x equals 2, x equals 3, x equals 4. This is the x-axis, that's the y-axis. But now, in our u versus y-axis, this is x equals 1. We're just mapping u to x according to this rule over here. X is this, u is this, and then x equals to the square root of u. So x in this case is when x equals to 1, u equals to 1. When x equals 2, u equals 4. And so on. So when u equals to 1, x equals 1. When u equals to 4, x equals to 2, and so on. So we've kind of stretched this x-axis here. And that's what the coordinate shift is really for this one dimension. Okay, so moving on to what Jacobians are in 2 dimensions, let's think of polar coordinates for a second. What our goal is right now is to find what is the area element, what's the fundamental area element in polar coordinates. In Cartesian coordinates, this is pretty simple. In Cartesian coordinates, the area element is just a equals dx dy. Since the fundamental area element in Cartesian coordinates is dx here and dy over here. But for polar coordinates, it's a bit more complicated. The fundamental area component of polar coordinates is a bit different. In polar coordinates, when you're sweeping through R to find your area element, you're sweeping through R like this, and then you're sweeping through theta like this. So what the fundamental area component looks like is this portion of an annulus. Now it turns out to find what the area of this is in terms of r and theta, this is delta theta, this is delta r, we can approximate this as a rectangle. This short side we can immediately see is delta r, but this long side, that's a different story. For this long side, intuitively you can see that this length is different from this length. That's kind of strange because that means this length on the rectangle would be different from this length, and wouldn't be a rectangle anymore. But it turns out as we make delta r and delta theta smaller and smaller, this side length and this side length approach the same value. And indeed the distance of this area element, instead of like being defined as the distance from this side to the origin and this side to the origin, it just becomes defined using one value, one number, which is r. And so basically our goal now, we figured out that all we need to do is find the length of one of these side lengths so that we can plug it in here and we can get the area of this approximation of this area element. And so we can find the area of the fundamental area element of polar coordinates, and then we can find the Jacobian. So using just the circle circumference, we can find that this length is 2 pi r times delta theta over 2 pi. So this becomes r delta theta. And now we can remove this question mark, so we know what exactly this is. It is r delta theta. And as delta r and delta theta approach 0, they become infinitesimal area elements. And so the area of this becomes r from here times dr times d theta. In this case, just as we found out before, this is the Jacobian. So when we shift integrals from Cartesian to the polar coordinates, we add an extra term of r in the integrand to signify this change of coordinates and to make sure that all of the area elements make sense. And now let's talk about the more general case. Let me not erase that. I'll put this to the side. So from polar to Cartesian coordinates, polar to Cartesian, we have certain conversions. So we have x equals r cosine theta, y equals r sine theta, and then we also have r equals the square root of x squared plus y squared, and we have theta equals the arctan of y over x. And in the more general case, the most general case, we can just define just functions which take you from Cartesian to that general case. And we use Cartesian as a baseline since the Jacobian and Cartesian is just one. There's no Jacobian. So Cartesian, let's just say general coordinates to Cartesian. We have x is defined as some function of the basis of that coordinate system, which is u and v, and y is defined in a similar way. And u in turn is defined some combination of x and y, and v is similarly defined. Okay, so now that we've got that down, we can start thinking about the fundamental area element of this general coordinate system. Basically, okay, let me tell you the motivation why we're doing this. We're doing this to find a general expression for the Jacobian of a coordinate system from Cartesian coordinates. So now what we have is, what we want to find is the fundamental area component. And it turns out, using Taylor expansions, we can approximate any fundamental area component in any coordinate system as a parallelogram that looks sort of like this. And what we want to do with this parallelogram is we want to find its area in terms of what we know about this coordinate system. So the area of a parallelogram, actually, let's just say that this side length is a vector A. This side length is a vector B. The area of a parallelogram, given theta over here and given the height, is the magnitude of A times the height. And just using some basic trigonometry, we can find the height is equal to b sine theta. So we have the magnitude of A times the magnitude of B times sine theta. And the astute among you will realize that this is just the formula for the magnitude of A cross B. Magnitude of A cross B. So this cross product between these two vectors is just the determinant of just this determinant. I, J, AX, AY, BX, BY. And I should just write this in general coordinates instead of X and Y. So A1, A2, B1, B2 is the determinant of that matrix. Okay, so now our goal is to find what exactly A and B are. And we can define A and B, and it's easy to see intuitively why it may be advantageous to define that as how the area, how the length elements dx and dy in the Cartesian coordinate system transform when we look at this transformation f and this transformation g. So what I'm saying is, suppose you have an dx in the I hat direction. We put it through this transforming machine, which is, in this case, which is f. Put it through f. And we get another vector out of it, which is where through this transformation, the dx the dx length element transforms to. And this dx length element, it has an x component and a y component. So we know that x can be written in terms of some function. So dx can be written in terms of u and v in this way, using just chain rule. So we have partial x partial u from here, and then the differential component, which is delta u. And these du's, delta u's cancel out. And again, we have partial x, partial v times delta v. And in the same way, we can write down dy, partial y, partial u, delta u, plus partial y, partial v, delta v. Okay, so we're almost done. We figure out how to write delta x and we figure out. Okay, so we're almost done. We figured out how to write dx and dy in terms of u and v, and now we can see that this is the x component of the transformed vector, so we say I hat, and this is the y component of the transformed I hat vector, so that's j hat. Now remember what we said before. The vectors a and b are just the transformed versions of dx and dy. And so we can plug in dx and dy into this determinant over here to find out what the scaling of this coordinate system is, and how you scale the dx and dy to find the area elements in this new coordinate system, which is basically what a Jacobian is. So let's plug this in. I hat, j hat, partial x, partial u, partial delta u, partial x, partial v, delta v, partial y, partial u, delta u, delta u, partial y, partial v, delta v. And this equals, basically we're taking the determinant, so we're just cross multiplying it. We don't need this I hat, j hat. So this becomes partial x, partial u times partial y, partial v, delta u, delta v, plus minus partial x, partial v, partial y, partial u, delta u, delta v. And factoring out the delta u, delta v, we get the Jacobian equals partial x, partial u, partial y, partial v, minus partial x, partial v, partial y, partial u. And as delta u and delta v become smaller and smaller, they become infinitesimals, we get du dv. And through this entire calculation, from parallelograms to cross products to figuring out how the dx, figuring out how the infinitesimal I hat component transforms to this transformation, and then plugging those values in back to the cross product, we found what the expression for the determinant is. We've derived the expression for the Jacobian. Let me write it more clearly up here. So this is the Jacobian for any general coordinate system. And let's test it out with polar coordinates, where u is r and v is theta, and x equals r cosine theta and y equals r sine theta. We have partial x, partial u is cosine theta, partial y, partial v is r cosine theta, minus partial x, partial v, that's just negative r sine theta, times partial y, partial v, that's sine theta. And then you can see how this just factor out the r and then distribute the negative sign. We have cosine squared theta plus sine squared theta, and that just becomes r. So now we've derived more concretely what the determinant of r, the determinant of. So now we've calculated concretely what the Jacobian of polar coordinates is. So thank you for listening to this lecture, and yeah, see you.